Alright guys, welcome to the final video of week 1, and I promise this one's going to be a shorter one. So we're looking at successive ionization energies. We've looked at what ionization energy is, so the energy needed to kick out one of those electrons, or, well, remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous 1+ ions. In successive ionization energy, what we're saying now is how much energy does it take to kick out it 1 more? And then 1 more, and then 1 more, and so on. And the definition will change ever so slightly depending on which one or which successive energy you're talking about. So if you look at oxygen in this example, you can see that the first one is our first ionization energy. It's the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous 1+ ions. The second successive energy is the energy required to remove 1 mole of electrons from 1 mole of 1+ ions to form 1 mole of 2+ gaseous ions, and so on and so forth. So each one is going to be in that same succession. Now, thankfully for you guys, the way to write these equations is the exact same as before, only now you're shifting where that positive is. Let me take you through the first one for helium, and then I will leave you guys to do the next task. So we're going to write down this second ionization energy for helium. So it's already had 1 electron kicked out, which means it's already 1+. Now we're going to remove another electron. So we put the energy in, comes in there, kicks the electron out. We now got an electron over here that's been kicked out. And what we've got now is a He, helium 2+ ion. What I'd like to do, guys, is I want you to pause the video and I want you to have a go at writing down the ionization energy for each of these. Note, when it comes to E and F, this is the third ionization energy. So this is going to be slightly different, but it's still going to be the same pattern. Right, guys, off you go. Hopefully you pause the video and you've done that. And now I'm going to move on to the next section. So now we're going to look at trends in successive ionization energies. To relate this to before, you've looked at the trends of the first ionization energy, where as you go across a period, you increase the nuclear charge, it gets more attraction, it's harder to remove the outer electron. This time we're looking at removing electrons from the same atom. So let's say, for example, we've got nitrogen here just like that. We're going to kick out an electron, it becomes N+. Then it becomes 2+, then 3+, then 4, then 5, then 6, then 7, and eventually we get rid of all the electrons. That should say 8+. So we've kicked out all of the electrons, and every time we do that, there is an increase in what we call the effective nuclear charge. When we add protons, we increase the nuclear charge, but when we remove electrons, we increase the effective nuclear charge. It becomes more positive, but that's only because we're removing more negatives, not because we're adding more positives. So it's still nitrogen, and we're just removing those electrons. So it just becomes less and less negative as we go through. As you can imagine, it becomes more and more positive, so the charge increases, therefore attraction increases, therefore the radius of it will decrease, and we're also eventually be removing the shielding as well. So that is just cars, but for successive ionization energy. So it could be something that comes up with the way they ask it. Now, if you can have a look at it here, this is the energy required to remove that outer electron. So this one is over here, that's how much energy we need. And then you've got this guy over here, that's how much energy we need to get rid of that last electron over there. Obviously, there's no electrons to remove in 8, so we can't have that one, because it's only got 8 electrons. So we're going to go down there. And what I'd like you to note with this is if you can look at the trend, it goes from 1 to 2 to 3 to 4 to 5, then, oh my God, 6, something happens, then 7, then 8. Now, we can actually compare this because there's a jump in the ionization energy between this point and this point. A lot of the times they'll want to know, why has that jump happened? Now, if we have a look at what's actually going on, we're removing those electrons. So you've got 1 electron, 2 electrons, 3, then 4, then 5, then we go to 6. So you can see between 5 and 6, we're removing that shell of electrons. So there's going to be a massive jump there for those last 2. So you can see here, I'm removing it from there, distance is quite far, easier to kick out, and then all of a sudden, we've got these core electrons that are right there in the center, and much, much harder to kick out. So it's going to be really, really difficult. And therefore, obviously, less shielding. What I'd like to do is, I want you to look at these questions here. I've got one here for potassium for you. So you can see here's the trend of potassium, and what I've done is I've highlighted where the electrons would reside normally in a potassium, so you can complete that, and then that will make it easier for you to answer the following questions. You can see here's just a trend of those. Right, guys, have a go at that and enjoy.